lead to get a more updates review on the same topic, but now focus on the Antarctic. So I combine this two into one presentation, and the newer one haven't published yet, but it's a review, so the content test is published paper. So in the context of sea level rise, we're focused on the polar region and why the tropical and the polar region is important in the context of our study polar climate. Here's a few motivation. The first is polar amplified climate change. So when our global warms and polar warms faster, and this is familiar gas surface temperature trends, and we see the Arctic warming much faster than rest of the globe, and Antarctic. And Antarctic has, pointer doesn't work with the screen. Antarctica has our own hotspot in the peninsula. And the zonal mean on this side, we see this is two sides of the pole have actually not warming up in the same rate if polar amplification of Y. The Arctic is much more or faster than Antarctic, and we notice there's a gap of the warming trends in the Southern Ocean, and so zonal mean we have a dip in there, so it's not surprise. The next things we see is in the sea ice. That's the temperature is reflect the second inconsistent polar response to global warming. The more inconsistencies come in the sea ice, the sea ice total extent in Arctic decrease dramatically, which makes its own climate change icon for the society. But in the Antarctica, sea ice extent over the satellite period is increasing. This is April time series of that in the both hemisphere. Sea ice extent time series ended in the 2014.
Is that a statistically significant trend in the Southern Hemisphere?
Yes, the increase in the trend is significant, and it becomes significant when sea ice data, satellite data accumulates, and particularly before 14, and there's period they are accelerate increasing, and I'm going to talk about in this, and another inconsistency is inside the Antarctic itself. The warming more happens in the peninsula and the West Antarctic, but in interior Antarctica and East Antarctica, this is split by the 4 seasons and all season. This is little outdated to 2006. The temperature published in this period, and with the accumulation of our data, and you will see this widespread of cooling become shrinking, but still the warming, the Western Pacific warming become more widespread, and warming magnitudes is increased. But even in that time, even in the 2003, one hand was telling us in the winter peninsula warms 5 times faster than the global average. So in the Antarctic itself, we have inconsistent warming. And this is more updated. This is the climate index, climate index 2013 to 17, and we still see, because this is widespread, the average smooth, we still see the blue part in the East Antarctic with cooling, but warming is more widespread, but the magnitude of warming is cannot compare with the continent in the lower latitude. So the next thing is inconsistent response to climate forcing in the climate models. When we put in the greenhouse gases in the model and ozone in the model, we see the CS response is reducing in a couple of climate models. But that is not observed because the observed CS extent is increasing. However, the air temperature CS in Antarctica have lots of spatial variabilities. So this is make Antarctica so unique and so different than the other part. So that make us thinking, what caused this inconsistency? Does tropical contribute to the inconsistency in the polar response, particularly in Antarctica? So today, that's why we are focused on the Antarctic today. Thinking the tropical polar, this remote connection, the first thing is coming to my mind is the ENSO teleconnection. So it has been long known the polar climate is strongly influenced by the tropical SST related to the ENSO phenomena, owing to ENSO's far-reaching impact on the many aspects of climate system, global climate system. Those are famous ENSO studies icon with temperature and precipitations respond to particularly El Nino, La Nino anomalies in the tropics. This ENSO Antarctic research can trace back to the early 80s, and in 80s and the 90s, people have systematically studied the connection mechanisms. So there are 4 mechanisms I list here, and is coming out in that early period of study on this topic. First is Rossby wave, and it's generated by the tropical convections. So when tropical has a warm spot, SST, this deep convection excites a Rossby wave going to both hemisphere to mid and high latitude. So the Crowley and Higgins and these authors is the first people displayed or discovered the phenomena, and of course there's more studies. And second is the jet stream change in response to tropical SST. So Chen et al. In 96 they find when you have a warm El Nino events, your subtropical jet in Pacific contract and enhance, and the Pacific the polar jet is weakened, retreated. In the Pacific, the jet stream split, and so you have the one enhanced and one weakened. Another group is think about the zonal mean circulation, the zonal mean on the zonal direction, the meridional directions, and those can respond to the tropical heat fluxes. And there's a whole list of people in that published paper on that topic. And that zonal mean circulation not necessarily always symmetrical around the globe. Some zonal mean, even it's zonal mean like meridional circulation, they have a basin scale characteristics, not necessarily symmetric. Another thing is the ID atmosphere transient ID activities and its distributions, particularly when you have your jet stream changed and you altered your storm distribution and ID fluxes distributions. So this is the 4 we call the traditional mechanism, and for tropical and Antarctic teleconnections. And in the next, I will talk about the last 10 years new advance based on the early studies. And you will see, even we find more type of we have lots of new discovery, but the basic convection mechanism still stayed with this framework. That never changed. So I gave you a little bit evidence on this for mechanism, connecting mechanism. First is zonally symmetric teleconnection mechanism. And Richard Seeger's paper on 2003 has a really good examples. And he did zonal wind in the 300 millibar first UF that pick out the major like westerly trade winds and all that. And he used that and regressed the zonal wind surface temperature on this first UF. That's it comes out with 3 or 4 seasons. And you will see the color is the SST respond to this zonal wind structures. And in the winter, this is a surface temperature, not SST. The warm of tropical Pacific have a corresponding to the temperature in the high latitude with the band structures, and the contour is the wind, zonal wind structures. And you see that's all zonal symmetric, increasing or decreasing through all that. And it's a symmetric, almost symmetric between the 2 hemispheres. You don't see too much of variabilities in the zonal directions. So this is one example of zonally symmetric teleconnections. And the second is this paper I published in 2004. It's good illustration for the asymmetric response in between polar and high latitude. This is particularly focused in Antarctic. And as we know, when this is El Nino examples, and when we have a warm tropical SST, deep convection, strengthening the Hadley cell, which was discussed by the Chen 1996 paper. And so when you're strengthening the Hadley cell in the Pacific sector, you contract it, and you also have a stronger ferrous cell, but the polar jet was retrieved. That's what we see in the data. And the same convection also excited the Rossby wave coming out to the southern high latitude in Amundsen Sea. This is a Rossby traditional Rossby pattern. So you have the convection in the shade area, and the wave goes to the both. In the northern hemispheres, PNA, and the southern hemisphere, SA. And landed in the polar ocean, corresponding to the warm SST is high pressure anomaly. And the location is in Amundsen Sea low area. And so that makes that low become weaker than the normal conditions. And this high anomaly produces local circulation, pushing the warm air towards the polar seas in the one side, and getting the cold air in the other side, and from high latitude to low latitude. So in the CS region, they generate 2 anomaly opposite phase in each side of this Rossby wave. And okay. Oh, here, yeah, okay. Yeah, so again, the same convection shifted the zonal circulation towards the east. So descending branches go into in Atlantic. In the normal situation, this warm patch will be in the warm pool area. So the whole circulation was shifting in that. So this is anomalous circulation. And this caused this tropical Atlantic relatively cooler compared to the Pacific. So then you relax the Hadley cell in the other basin. This is an example of ENSO change mean circulation, but still have basin differences. It's not zonally symmetric. And then you have a weaker Ferris seal. Remember, this is a stronger Ferris seal and weaker Ferris seal. So you push the lower branches, mean circulation, moves the warm moisture air to the polar region. It becomes stronger in the Pacific side and weaker in the Atlantic side. And those are the meridional heat transport into the CS region. And associated with this, even the warm SIC gets stronger Hadley sail in the Pacific. The jet stream contract move towards to the lower latitude, but it doesn't happen that doesn't happen in the Atlantic, South Atlantic. The jet, there's no split jet, just one jet just moved to the polar, and that gave you the storm distribution altered in response. So this figure summarizes probably most all the mechanisms in what we talking about connect tropical to the highlight, except the Seeger mechanism, the zonal wind band structure.
You think that stratosphere modulation is
Yeah, the stratosphere modulations, stratosphere connecting tropical to highlight is one of the new discovery in the last recent decade. But it's not go through affecting jet. Jet is in the top of the troposphere. It's affecting, particularly in the northern hemisphere, is southern stratosphere warming, the activities that can connecting the tropical to the high latitude. Yeah, that's southern hemisphere thing. That's is the one of the things we need to further understand what is the polar mode, polar process interacts the remote forcing, generate anomaly in the high latitude. This is still need lots of work to it's still a scientific question, and people start discover some of, but not all of that. But there are lots of processes remain for us to further to understand. But that's very good questions, and so the new advance in the last decade come from I organized them into the different timescales. Firstly is the intraseasonal timescales, which is MGO. Happened in the tropical Pacific, MGO has this phase across from tropical Indian Ocean all the way to across the Pacific, and they have a preferred windows to get the tropical signal go out. It's in the eastern Indian Ocean and far western Pacific, which is their phase 4, 5, 6 in that range. And the MGO with their strong convection, their signal they can generate Rossby waves go into the high latitude Arctic and Antarctic within a few days to a week. And within a week, I think in a few days they can disturb the atmosphere circulation. In a week, you can see in the surface temperature change and CS change. And they also can, in addition to the Rossby wave, they also can change the zonal wind respond, and also they can disturb the stratosphere. More of this study focus in the MGO with Arctic polar response, and a few talk about the MGO with Antarctic surface temperature and CS response. But the signal is very patchy, and so I think it's these groups in Penn State University. They published a series of paper on that topic, and one of them is come back to the Southern Hemisphere. The second one is in the interannual timescale. Basically, is the ENSO. And what the new discovery is the connections between ENSO, different ENSO flavors. So people find that there's Eastern Pacific El Nino and Central Pacific El Nino. Their connections are slightly different because when they generate Rossby wave, if the source of the convection shift in the tropic, and your wave pattern going to shift all across the hemisphere. And so Eastern Pacific and the Central Pacific landed the anomaly pressure center in the high latitude at the different locations. I will show you some evidence. And also, they particularly in the Southern Hemisphere, people find there's a preferred season. The teleconnection was much stronger than other seasons, and the stratosphere convection at interannual timescale also found it's more look like you connect to the more study focus on connecting to the Arctic. What else? Yeah, the tropical forcing is outside of tropical Pacific. Before interannual, we all focus on the ENSO, it's at the tropical Pacific. Now we know in tropical Indian Ocean can accept Rossby wave too, and tropical Atlantic can do that too, and even North Atlantic can do that too. And ENSO influences not stay at the surface. It goes beyond the surface. It can go influence can go to the 3,000-4,000 meters below the surface in the deep ocean. And so those are the new advances at the interannual timescale. And the next is multi-decadal timescale, which is we often see the climate trends in instrumental period. And so this is more relevant to this series of seminars, and the rapid warming around Western Antarctica and Antarctic Peninsula over recent decade originated from a tropical region. There's a whole line of study focused on it, and today I will probably spend more time on this one. And paleo, we also look at the paleo in our published paper. We look at the paleo perspective referred from proxy data, and this is pretty difficult the task because the proxy data is too sparse and very hard to get the detail of the connection pattern or mechanism out. But even our modern current present climate can provide some clue to the paleo data and the possible polar influence to the lower latitudes during Ice Age when polar CS extend much further equator wall. That's probably the largest. It's not tropical continent. Highlighted is highlighted one ice cap on the land, on the sea, all pushed to the lower latitude. And then you change, you alter the variability in the Pacific, but the IGCT may be moved to further south. And the North Atlantic cryosphere and the ocean impacts on the tropics and Southern Hemisphere winds. And with rising CO2 and when we recover from the Ice Age maximum, so there's a signal we can trace back from a proxy data with all these people. This is a modeling study, and other people is a proxy study. So, but I think today I'm going to give you some evidence in this to focus more in multi-decadal timescale. So this is the example of different El Nino connections. This is Eastern Pacific. We can see very clear. This is the pressure anomalies. Eastern Pacific, we have this diagonal wave coming into the high latitude. Anomaly pressure center is in Amazon Sea low, but in the Central Pacific, this trend is coming from further east in this. And the pattern of the Central Pacific, Eastern Pacific, and Central Pacific, and you can see your warm SST, that kind of excited Rossby wave are in very different locations, and so they generate a different response. This figure, this study done by the Gina Kirkman in 2010 was illustrate how the how the season differences in respond generate Rossby waves. They break down 2 months, average 6 panels through the year, and you can see when the Rossby wave counter its pressure, and this is the Rossby wave come in the September, October, Austral spring. They already, before the ENSO El Nino become mature, they already start, right? Because you already have a pretty strong of SST in that season, start generating the Rossby wave. And but even if this goes to the winter, you respond in the northern hemisphere so strong, but in the southern hemisphere become weaker. So it's not, it's really, this Rossby wave also works with hemispheric seasonalities. So they conclude the Austral spring as the favorite season for southern hemisphere receiving the Rossby wave propagation.
Just going back one slide, you showed the different connection pattern for
Yeah.
Central Pacific warmings and
Yeah, this Rossby wave coming down is not that significant because of the Central Pacific cases is small. The not small, but is a few. I think the Central Pacific is a recent decades getting more and more of center. Before most of the large El Ninos coming in the Eastern Pacific El Nino. So the
Central Pacific events are weaker and then still that's ocean not as strong as actually.
yeah, that's that's basically what these things. It's not as significant as this. This is another wave trend going to not influence the Amazon's lower going to Weddell Sea in that. But in this paper, some of our mainly they conclude this is the wave trend coming out from central El Nino events.
Is there a simple explanation? Because it seems like with the Central Pacific events, the convective anomaly is farther to the west, but it seems like the wave train is actually, especially on the latitude of the Amundsen Sea, it's actually off to the east.
Yeah, I don't think they have a really good explanation in there.
Okay.
They are
Seems like it's statistics.
yeah. When I reading this, I haven't really found better example for separate. But when I put this figure in, it talk this, it took me a long time to understand what they're talking. They're actually talking about the non-significant trip, but it's in there. What's happening with which I think if there's a longer consensus. And also, they didn't explain why there's another wave transit for the east. This is, but this is one paper most directly addressing this problem. There's other paper was kind of hinted and was not good. I think it's not too difficult to run the model experiments to choose a different source.
Right. Right. You have to have a model that you do difference between these
Yeah. Okay, so so now we move to the ENSO impact beyond the surface. This study we did with McKee. Darren McKee was approved by the student just like recently, and he did that as undergraduate intern in my group. We did start from learn how to run MATLAB, how to read CS data, And he did this for 2 years of his undergraduate senior research practice period, undergrad RD student. And he ended up writing this paper as first author. And I said, if you write, you'll be a first author. And he said, I will do it. And so, and this is a really nice piece of study. What we use is Arnold has 2 moorings in Weddell Sea bottom water exit. And mooring 2 is in the 3,000 meter, mooring 4 is over 4,000 meters. And they record temperature slightly change over a long time. This is their time series. And we see there in the 2000 and 2001, we have a very positive anomaly in there, and then we have a cold spell in 2002, and then temperature anomaly become small without a large signal. So we trace back what could cause that, what could cause the warm pulse and cold pulse. So we trace to the surface, and we see we have here is the CS at the surface in this area in the coast. In the solid is the CS. We see in the CS we have a larger anomaly, a little bit early, many months early than we see the warm pulse. And we have positive winds before this cold pulse, and then it's a reverse. So it happened in this different shading as 2 opposite phase. One is positive wind, offshore wind, and less CS, and then it's onward and more CS. And then we find why the CS and the wind are different. So we trace further back for larger scale drivers. And we found that there's a period of time, and even leading this local wind and the CS is the ENSO, meaning 3 dashed line on the top here, and the sun solid line. And in this, when we see a large anomaly with fixed leading time, and we see the ENSO and the SAM is opposite. So when we have La Nino, we have El Nino. La Nino positive SAM and El Nino negative SAM. So finally, we are looking at the surface and all that, surface wind distribution curls, and when we find in El Nino and negative SAM produce the same wind pattern with both. And La Nina and positive SAM produce same phase but opposite than the early case, the wind and the CS. So that wind surface wind anomaly change in the ice distribution. And so if we have if in the summer we have a stronger offshore wind, we push the shelf area, the sea is open, the ocean is more open, and in the winter we have a large room to grow. The sea has grown more, and the wind strong possibly grow more, and there's much more brine rejection in that situation with stronger meridional winds. If wind is small, and this is area in the summer, we still have a residual CS, and the CS still covered most of the ocean, and in the winter the ice start growing and filled up, and you don't lack of a strong wind, you don't push it away, so you stop the CS growing very quickly. So you grow less CS, you have less brine rejection. So in this case, we produce more high salinity shelf water that can sliding down with some residual time, resident time on here, and then they slide down to the continental shelf and follow the Weddell circulation and then move to the exit point. And then you observe the cold pulse, that's freshly made cold shelf water coming down to there. And in this situation, you do not have the enough of dense water, so you have less extra water export, so you see a warm pulse. So this study is probably the first few detect the ENSO signal in that deep ocean. And another very good outcome from this study is we find the CS, the El Nino and the La Nina, when they are out of phase, they produce the same high latitude anomaly. So they reinforce, their effect reinforce each other, and that reinforcement make a stronger anomaly in the polar. So these things later being discovered by other people, not later in the same time. See, Fawcett et al. In 2011 did this study. They focus on atmosphere circulation. They are separate the impact on the pressure field, impact on the sea level pressure from El Nino SAM out of phase and ENSO SAM in phase. So there's two scenarios. And the first, they just look at they do all the composite analysis. This what colored here is a significant anomaly, and the contrast of the pressure anomaly. And positive SAM, we know the low pressure and high latitude pressure, and the latitude and low pressure in the pole. And the negative SAM you reverse. That's very understandable. And here's a La Nina. And in the high latitude, we have the low pressure here and high pressure on the continent. And El Nino warm events, we have a high pressure center in Amazon Sea Low, like I saw the teleconnection figures. Now we start make a combination, La Nina and the positive. You make this Amazon Sea Low very strong. It really standing out. And this is the one, this low affected the peninsula temperature, West Antarctic temperature, and affect the CS, Antarctic dipole patterns. And you are another, this is out phase negative SAM El Nino. And you make this stronger, significant high pressure centers. And if you do they call it in phase is La Nina and the SAM negative and El Nino SAM positive, and you cancel out the effect on the anomaly signal. So in this area, you have a weaker, but still some processes dominate, but the anomaly center become weaker. So this is the one study telling us the tropical response and high latitude, when they interact, there's interference, wave interference, or anomaly. Either you can reinforce each other or you weaken each other. And in 2008, Stammer John is also one of our students, has this study used much shorter, less cases, but she found the same pattern. The SAM positive La Nina, she has 3 cases that produce the strongest Amazon Sea Low in there. And other, this is a reverse, positive SAM and La Nina, without the La Nina. So if you do without an El Nino remote forcing, this low doesn't really in there. But if you have a negative SAM with El Nino, we have some low, but the El Nino effect weakened that low. Remember, El Nino produces a positive anomaly pressure center in Amazon Sea Low region. So this is clearly indicating you need the right phase combination, you get stronger response. This study is indicating not only tropical Pacific excited Rossby wave going to influence Antarctica, and this we are looking at we're looking at the Indian dipole's influence. Indian dipole is this in Indian tropical Pacific reverse the temperature SST anomaly. But more frequently, if we extend this all the way to the Pacific, this most frequently become 3 poles and all co-vary with El Nino events, ENSO events. Most of them, only a few cases is not. And what we did is SST and the CS field, we conduct SVD analysis. We pulled out the leading mode, and then we use that leading mode to regress the pressure and the winds, the fluxes, Rossby wave fluxes, with that SVD1. SVD1 pulled off the largest CS responding to the largest tropical SST response. And they are very similar to the Nino 3. This is a regression to the Nino 3. These two patterns is very similar because, and also this one, is Indian dipole. These 3 are very similar because Indian dipole is co-vary with Nino in the tropical Pacific. So we do large signal is all pulled out in the tropical the Western Hemisphere here in Amundsen Sea low, which is dominant signal from ENSO events. So we like to do a partial correlations with IDO, correlate all this field with IDO with the Nino 3 removed. Then we see something different, that this Western Hemisphere become weaker and the energy, wave energy flux coming down to the high latitude much early and before this energy flux is away from Antarctic coast and right now it's coming towards. So if it reflected into the CS field, it's the same 4 things, the correlation, the first 3 SVD1 and Nino 3 and IDO, IOD index, so we have generally the same CS response, all dominated by the ENSO influence. However, if we remove ENSO, the anomaly in the Western Hemisphere weakened, and in Eastern Hemisphere, in the Indian Ocean, they're standing out. And this schematic shows how the wave trends. Actually, we should draw another from the Pacific. The Indian Ocean wave trend join the Pacific wave trend, make the same high in here. When they have 3 poles for tropical India in the Pacific. But if we looking at the Indian dipole only without Pacific ENSO signal, this wave trend move toward propagate more close to the Indian Ocean coast and generate anomaly circulation that impact the CS anomaly. So this is intra-annual variability. This is new advance in last decade. And now we move on to the multi-decadal changes in Antarctic Peninsula and the links to the tropics. And this is air temperature and long-term trend, and air temperature is outdated in there, but as I said, if you look at most updated data and the spatial distribution could change, but the story still stay the same. We have a stronger warming in the Western Pacific and in the peninsula, depending on each different season, you see different strengths of the warming. And that's in the air, in atmosphere temperature. And if you look at, into the ocean, this graph is the global ocean in 700 to 2,000 meters in that subsurface meter heat content average. You see this average going, this is the line going up over from 1960s to 2010. And what's the bar here is indicate in the Weddell, in the Amundsen Sea outside here. So outside in the subpolar sea in Antarctica, the warming rate it matches global warming rate. So our ocean, even we are protected by ACC and inside the polar GR, our subsurface ocean is warming up at the same rate with global subsurface. That's the temperature in the atmosphere and the ocean. Here is in the Antarctic cryosphere. And this is the relative update CS trend, and red color is decreasing and blue color is increasing. With 4 seasons around Antarctic, we see the largest retreat is in Amazon Sea and Barneham Sea, Western Antarctic Peninsula, and the increasing dominated in Rossby. And even before this paper used data to 14th, Stammerjohn did ice cover, ice advance and retreat time series, and also that can produce ice cover season. And she found in the Barneham Sea, the ice cover season shortened by 3.3 months during the period of, I think it's 2011, 79, it's covered by my movie image in there, to 1979 to 2011, for that pure satellite period. The ice season is already shortened by 3.3 months. That's a very significant reduction. Now we go to the glacier ice, and this is ice shelf, and this paper published in 2013 right now, showing the ice shelf thinning, contribution by the basal melt in the black, and front break off in the white. And so you see the large ice shelf, loosening ice shelf masses in this stretch. Some big in Weddell Sea and relatively smaller in Antarctic, East Antarctic. And in Potter's 2018 did similar those different satellite data, and conclude he said the ice shelf in the Western Antarctic loses increased by 70% in the past decade. That means in the past decade we have accelerated ice shelf melt. And early value gained by East Antarctic ice shelf seas. So some place in the early days we see ice shelf in East Antarctic gaining the mass, but that gaining stop. So regardless, we have a strong spatial contract, but ice shelves in general is losing the mass. And the last is the land ice, the ice sheet. This is the great data, and you see the majority lose the land ice in the Western Antarctic. This is not some news for this group, but from cryosphere and atmosphere and ocean we see in the Western Antarctic has a systematic change, all coherent with warming and losing ice. So the question is, here we have a few notes want to mention before we say next step. The Antarctic land ice melt have two actually very distinct characteristics. So one is accelerated melt. It's melting faster in recent decades. It's discovered by the Manet of the authors, and also strong asymmetric melt, as we just showed, melt rate in Western and Eastern Antarctic. So accelerated and symmetric of Antarctic land ice melt cannot fully explain by the greenhouse gas force. If you put that into a climate model, you might not get those, and then maybe attributed to the regional change in atmosphere and in ocean. And this regional change can be connected to the remote forcing from tropics. And so those a number of people make that connections. So the scientific question, next scientific question is, why this systematic change are localized in the region of Antarctic Peninsula and Western Antarctica. So since we're talking about the multi-decadal timescale, outside of Antarctica, other large climate variability at that timescale will be the interdecadal Pacific Oscillation, before they called PDO, and another is Atlantic multi-decadal oscillation. So these are the potential driver, but how they drive this change in the higher latitude, people have make some connections. So this being in the SAC 2013 paper gave you a hint on the peninsula warming. So they did SVD analysis between the tropical SST and air temperature in the peninsula. They find that shape, there's a warm in the western and cold in the tropical Pacific, and they also find associated pressure field indicating that the cold Pacific have generated Rossby wave, generated low pressure center in Amundsen Sea low, and you see this surface temperature and SST. These two curves, when they do SVD analysis, they covary on interannual time scale. They also have the same trend, long-term trends. They are indicating that the long-term change is associated with tropical Pacific SST pattern.
So, I'm confused because I guess earlier you were talking about the flavors of ENSO.
Yeah.
Southern Pacific warming.
Yeah.
That doesn't do very much in the Amundsen Sea. It seems like it's Central Pacific cooling and it's having an effect in the Amundsen Sea.
Yeah, this is what we're talking about. Air Nino's up and down interannual abilities, and this signal is dominated by the trend. By the trend, and so before we have a warm here and warm here, and we have different locations and we have isolate the change. But this one, I think, I believe that they are claiming the long-term trends playing the role of that, and
So I guess I'm just wondering why the mechanism for your annual variability doesn't apply to long-term trends. Like what's different about multi-decadal variability that you're not rating the Rossby waves out of a convective anomaly?
there are background Rossby waves, accumulated Rossby wave generate this shape. The Amundsen Sea law anomaly is very sensitive to the change in the temperature in the peninsula and the West Antarctic. If you shift a little bit, you change your warming up or your fluxes, horizontal fluxes up in a different location. This is the shape they are generating. The warm air coming to the peninsula, and they didn't show this extended. I believe if they show the whole West Antarctic with this one, it's all caused West Antarctic warming too. But this analysis, they isolated their data in the peninsula. They try to see what happened to the peninsula, use the localized data. But this pattern generated by the long term, and it's similar. They still claim that it's Rossby wave, multi-decadal time scale, and which can be left beyond the up and down of interannual variability. That's the residual part.
Right, I'm just thinking if it's 1 year ago, and obviously that's naive, but
Yeah.
if it was 1 year, then you would just expect to get the same pattern that you got for some percent warming and cooling, just that you would
Yeah.
filter
Yeah.
out the driving, the time series for that, and you get the same spatial response.
Yeah, I think it's more clear. The Central Pacific, they were seeing is moving a little bit more than that direction. And then you see next study, they come out with the same things. And it will connect it. But this one is kind of in the between El Nino response in here and the multi, like the Central Pacific response here. it's sitting in between. I think lots of things is depending on which period of your data covered and how many events you covered, and,
Sure.
and you will see in the PDO.
I'm just a bit concerned. We're running out of time slightly.
Okay. Oh, sorry.
No, it's fine. Do you have much more material?
I can summary. Let's try to finish in 5 minutes. And here's another one. The study. It's use. This is a really trend analysis study. Snyder, and they find the tropical influences of PSA generate this pattern pressure and sea ice and air temperature. But this is Amundsen Sea low. The local trend. They have the exactly same pattern and the same magnitude. The story behind it is this anomaly low put the heat into the polar region. Generally, the warm temperature also reduces sea ice. And then when you reduce the sea ice, you bring more of heat from ocean and warm the atmosphere more. So they claim sea ice and positive sea ice and atmosphere play 50% of influence. So, and this is right. This is the mean sea level trend. You see, if you look at the trend, and you see this very broad Amundsen Sea low, with the center in here and in here. This is the multi-decadal signal. It's slightly more than being stacked into here. And this is ENSO. ENSO move towards here. And this is a PDO. So basically PDO responded to the long-term trend. And so when we look at these 3 studies, Snyder's, I think this is the reason very sensitive can generate the elongated Amundsen Sea low. And here, but the tropic behind it is an anomaly. This is C-shaped anomaly in that, here, the color is SST coding here. And even this one, this is air temperature. And then you see your warming West Antarctic and Peninsula more related to this C-shaped tropical SST. And if we look at SST, signals long-term trend, zonal wind and SST, you see this in the data, long-term trend just look like that. And if you use this in the simulation model experiment, you put full forcing in here, and you put the tropical Pacific, you do generate zonal wind. This is a wind response, very strong response. And you put ozone, and you without the tropical, you also make a stronger zonal winds. And all other forcing doesn't have this response. So tropical and ozone produce a stronger zonal wind westerlies outside Amundsen Sea. And so what that help you? What does wind means? Wind means stronger wind. They can put out more of CDW water coming. That's by the Steiger's 2012. So if you put all this study together, you find not only atmosphere anomalous transport, and also zonal wind. Particularly this zonal wind in the Pacific side is 3 times than the global average. And that happened in that location that produced. This is Atlantic response. It's the similar things. The polar Antarctic response to the North Atlantic. Due to the time, I will skip that. So, tropical driver. Right now, we have multiple people saying the tropical Pacific drives the tropical Atlantic. Some people say tropical Atlantic drives the tropical Pacific. But what is the bottom line is the last paper by Lee is saying the EMO also produced that shape of Amundsen Sea low. So both IPO and deepens Amundsen sea low and lead to surface warming. This is one answer to the why it's isolated. The chain is isolated in the Western Antarctic. And what causes the melting the Antarctic? It's really surface melt and reduce the mass and also lubricate bedrock moving faster. If I see moving faster, that's one mechanism. And low sea ice lead to stronger ocean wheel, not only more of heat to the atmosphere, they also more dynamically impact on the ice shelf, so it's more easy to plan. And the circumpolar deep water, this is another way to telling you that why it's isolated in the West Antarctic. Is they are all increasing, but in the Amundsen Sea, they are more easy to go on to the continental shelf. In contact, the glacier make the basal melt, but in the eastern Antarctic, this water was locked away from continental shelf. They are not easily to get into. So this is another answer. Okay, let's skip we have a story to talk about why the sudden change of sea ice, and it's also have a tropic impact due to the time. Well, I'm not going to talk about that. So here is the summary. AP warming in Austral 4 and West Antarctic warming in Austral Spring is related to the tropical SST, to the long-term change. Warming in the Western tropical Pacific, cooling in the Central Pacific. This is consistent the pattern from different studies. Western Antarctica winter warming is related to tropical Atlantic and North Atlantic SST. And the Rossby wave trend emanating from tropical still dominant, the mechanism connecting to the high latitude. And the last three is basically what come out of this review is how the tropical ocean interact with each other remain a scientific question. And we don't really know if all the tropical region is independent or connected. Some is connected, some is independent. And how the tropical influence from different tropical regions, when they all come to the high latitude, how they interact with each other. What is the resulting? This is remain a question. And how the tropical force respond, interact with high latitude volume. We know some, but we don't know all. So this three is what we come out, what the future study needed to address. Thank you. Sorry for taking too long. Question?
So, do we have a simple, I'm sorry. So do we have a simple explanation of why the sea ice had increased over West Antarctica and Southern Hemispheres in the last few decades? Is that just related to the Annular?
No, the PDO, the long-term trend, they have this elongate of Amundsen sea low. They make this the polar cold water coming out of the Ross Sea and continues coming it's increasing amount. So the Ross Sea generates much more of sea ice than any other places once you have that. And what I didn't see is the IPO. There's a 3 time series. The last story I didn't see is the one that PBO is inactive. It is low in high latitude, so it's persistent in the long and generate. That's the time you get. That's the time you get this. This is a PBO in the negative phase. This is a PBO in the positive phase, and this is PBO. But we don't know why this slight increase in the PBO positive, but we do know the accelerated increase of CS, and that is PBO becoming active phase. And when they suddenly change to the in 14, they change the PBO change to the positive phase. They this whole thing is prepared the subsurface water come to subsurface in polar region, but I cannot push in the cold water in the surface, so you got this surface water generating more ice. But when they collapse, and suddenly they change in the 2016, SAM changed the phase to positive to the negative, and then combination of these two, and ocean's subsurface warm temperature going is present here, making this is in this period. So polar is very cold. But this is a 16, 17. This is a temperature, ocean temperature with steps and with years, zonal average. So you see in the 16, 17s, the warm water come from surface to 600 and all pushed to the polar sea. And that is what happened as PDO become positive and suddenly sun become negative. So at least the people, there's a whole bunch of hypotheses in there just studying this drop and try to skip that. But this is a Nino in the 2019 last year's paper, have a more systematic investigation like this.
So shown some slides emphasizing the importance of the Central Pacific.
Mm-hmm.
And so Central Pacific system. So is the Pacific not important because it didn't have decadal variability, or is it because an SST anomaly in the Pacific could have less influence on convection because it's cooler there, so it takes up larger anomalies and you get to a convective state?
Yeah. I think Eastern Pacific El Nino, the largest, two larger 1982-83 and 1998. Two largest is all the way to the east, have the largest air temperature, and that responded to the make the Rossby wave propagate to the high latitude, no doubt about it. But because it's pushing the largest pushing it all the way to the east coast, they are moving their regular Rossby wave to the west. And then in Antarctica, Antarctic dipole is the one responding to the El Nino. And they're supposed to be lies in the Pacific, more in the Weddell, but because of the Rossby wave further west, they move this anomaly further west. So if you look at the El Nino response, you see inconsistent. But the La Nina response is perfect consistent because La Nina cold SSE always in the central Pacific. You never have a really one you put eastern. So when they come to this our 2001 paper, it's very clear. Every single La Nina event generated more CS in the Pacific and less CS in the Weddell Sea. It looks like a repeat each other. You just put every raw data in there, they are repeating. But this reverse the ice edge anomaly in response to the area because they varies. And so sometimes the positive is here, sometimes positive is here. So you average all the events, your anomaly seems smaller. It doesn't. It's Central Pacific is the one more consistent high cold anomaly. And sometimes right now it's having more of a warm anomaly. But the largest, the last, at least from the instrumental record, the largest is always in the east. So they also generate large anomaly, just not in the same location as the rest of it. So make our high latitude response a little bit different.
While you show a trend, there is a trend in the Southern Hemisphere with sea ice increasing.
Yeah.
The more obvious thing for you is the variability.
Yeah.
Is that variability driven by this La Nina?
Yeah, lots of variability driven by not necessarily hemispherical average, but in the Western hemisphere, you have the largest response. CS anomaly is responding to the However, the responder is one side positive, one side negative. When you average them together, you become not very long. And the consistent is elongated. Low pressure center associated with negative PDO. It's always pushing the cold air from western Rossby and consistently over the years. So that's most of, at least up to 2014. That's the very fast acceleration. This is in this when we have time series going to here, the Antarctic sea ice extent increasing is marginal significant because of some seasons significant, some seasons not. Until we get to here, suddenly all seasons become very significant. The increase is increase, no doubt about that. It's significance from 90% increase to the 95% for each study. So this is coincide with so I think the evidence is pretty clear at this point.
Any other questions? Should we thank the speaker? In the interest of time, should we thank the speaker again? So, is anyone interested in going to lunch, perhaps? For the discussion? No? Thank you.
Yeah. Thank you. You're awesome. Yeah, we are writing a new paper, still review, but our other paper is review the teleconnections both hemispheres.
Right.
And focus on the last 10 years of new advance. And right now we are focused on Southern Hemisphere with a large amount of new discoveries. So it's really short period, but